there's something a bit of a puzzle because, here we have a physical quantity which has some kind of singularity, right? Or at least, its derivative has a singularity. Now, in everyday life, we don't actually associate singularities with physical quantities, right? So, so what is happening? So, what is happening is essentially, if you look at, say, Z, the expression of Z, but look at it in terms of the value of n, then you can show that it's 1 minus 1 over n plus 1 minus t over tc, 3/2 of 2 minus 1 at t divided by t, so below tc. Now, if I take, right, so this is below tc. So if you look at what tz by tc is, above and below, tc, what you see is that there's a difference below and above by a factor of n, 1 over n. And that this goes to infinity. Sorry, so this goes to 0. Hang on. Right, sorry. So the idea is so the derivative is of order 1 above tc. So this guy is of order 1 above tc, and it is of order 1 over n below tc. So as you see, as n goes to infinity, this goes to 0. So the if n was not 0, then these two things would be smoothly joined at t equals to tc. So the problem here comes from the fact that we are actually taking the number of particles to be infinite. So this is a lesson that is actually very robust, that goes over to all physical systems, is that phase transitions can only happen when the size of the system becomes infinite. So for finite n, you will never see a phase transition. Right? So in real life situations, we see phase transitions because the number of atoms and molecules is so large that it is effectively, we are in the thermodynamic limit. Okay, so that is probably, so I mean, in conclusion, I would say there are two very, very main lessons from it. One is that some physical quantity or its derivative is singular at a phase transition. The other thing is that phase transitions only occur in the n goes to infinity limit. Okay, so any questions?